Alright, so welcome to the curve sketching video. What we're going to do is use analytical methods to see how we can identify the shape and structure of a specific function when we graph it. And then we'll use Python to confirm our work with AI. So our function for this video is going to be x cubed all over x squared minus 3. Right, so we want to think, okay, what kind of function is that, right? We know it's a rational function. Now, not every function is going to fall neatly into a specific box. A lot of them are compositions of different types of functions, but this one is definitely irrational. The first thing we want to do is find the derivative, right? And so we're going to have our f prime g and our g prime f. So we're going to put our f as x cubed, our g, let's call it x squared minus 3, right? G prime is 2x, and f prime is 3x squared. Okay, so our f prime g minus g prime f is going to give us 3x squared times x squared minus 3, can't forget those parentheses, minus g prime f will be 2x times x cubed. We'll divide all of that by x squared. Where simplify terms. Alrighty, and we end up with 3x to the fourth minus 2x to the fourth. Right, so that's going to be x to the fourth minus 9x squared divided by x squared minus 3 quantity squared. Okay, so again, the x to the fourth terms are here, like terms, you subtract them, then minus 9x squared. So we end up being able to factor, right? And as you sometimes as you work through this curve sketching worksheet, in order to find those zeros, we gotta factor it out. So we have x squared times x squared minus 9 over x squared minus 3 quantity squared. Okay, for the numerator, we get x equals 0, x equals plus or minus 3. Right, when we have the numerator equal to 0 for the denominator, we get x equals plus or minus radical 3. So that's going to give us the zeros of the numerator, the zeros of the denominator. All right, f double prime means we need to find the second derivative of the initial function, or the first derivative, the derivative. So our f is that, our g is that, and so what you're going to see very quickly is you just got to be quick on your toes as far as knowing how to find derivatives, which rules to use. Like you see this one right here, and it's like, okay, that's definitely a chain rule. That's the point of everything we've done up to this point, right? To have that facility in terms of knowing which tool to use in your derivative bag. So that's 4x cubed minus 18x. All right. And so I'm going to write this as 2x 2x squared minus 9. Okay, and then write this as 4x x squared minus 3. Okay, now as far as the quotient rule, we'll have f prime g times g prime f okay. Now this piece right here is f, one factored. If you don't understand it, press pause and just double check that. Okay, so that's my f, and then I'll put my g right here, and then my g prime right here. Okay, so the thing about it is, if you are able to factor once you find your f prime and g prime, do that at that point, it'll make things downstream a whole lot easier for you. Square minus 3, quantity squared. Why? Because you know that the whole point is to find zeros, and so therefore you will be factoring the numerator. So you got to put it all together, right? Before we were content with just leaving your answer something like this. But unfortunately, or fortunately, depending on how you view life, this is not going to suffice. And so we're going to need to combine terms in the numerator, find like terms, and do all that. That is algebra, okay? And so I'm going to let you work it out, okay? But just notice that here and here we'll have a 4x cubed, right? So there's the x terms, okay? And I'll let you know what we end up with. There's going to be 2x that's going to be common in terms of the x terms. In this term and in this term, there'll be the x terms, right? So the x terms, the most we can get out of it is a 2x. Then there's going to be the x squared minus 3 terms. I see I have 1 here, right? And then I have, actually should be 2 for my f prime g. So I have 2 here. I'll be able to factor out an x squared minus 3. Okay, when you factor that out, then you see what you're left with, and what you identify is you'll have a 3 times x squared plus 9. So I'm running out of space, so I'll put a x squared plus 9. And then I'll put a 3 over here. Okay. All over x squared minus 3 to the 4th power. That ends up being 6x, x squared plus 9, all over x squared minus 3 to the 4th power. All right, so then the zeros of the second derivative end up being x equals 0 from the numerator, and hopefully it's very clear, this part has no zeros. So the only zero of the numerator is x equals 0. Denominator has the same zeros as before, plus or minus 3, square root. All right, so when it comes to curve sketching, the first thing you want to do is say, okay, what is my function, right? What is my function? What is its derivative? What is its second derivative? And once you do that, identify what the zeros of each are. Now we found the zeros of the first derivative, both the zeros of the numerator and the denominator. We found the zeros of the numerator and denominator second derivative. Now we'll do the same for the actual function. Okay, so for the actual function, it is equal to x cubed over x squared minus 3. Okay, the zeros of the numerator, if x cubed is equal to 0, the only way that can happen is if x itself is equal to 0. Got that. Now if x squared minus 3 is equal to 0, here we are again. And so x equals plus or minus radical 3. Those zeros are the denominator. How do the zeros of the denominator help us? Well, it helps us identifying what the domain is, right? So the domain will be, let's call it D, set of all x's such that x is not equal to plus or minus radical 3. Set builder. right? In interval notation, it will be negative infinity to minus radical 3 union negative radical 3 to radical 3 union radical 3 to infinity, right? So when we're looking at the entire number line, we cut it at 2 spots. I'm not trying to do all that. Right there and right there. And so those are the places we have gaps. Everywhere else is part of the domain. 1, 2, 3 pieces. 2 cuts, 3 pieces. Okay, that's domain. The next thing we want to talk about is intercepts, right? And so intercepts are locations where x is equal to 0 and y is equal to 0 because we're touching the axes. So the y-intercept is where the function crosses the y-axis. So what do we need to set equal to 0? Correct, we need to set x equals 0. One of these days I'm gonna figure out how to touch the screen without it tripping, right? Anyway, so that's what we do. Set x equal to 0, then we will find the y-intercept. So our function is f of x is x squared, x cubed over x squared minus 9. So our function is x cubed over x squared minus 3. F of 0 is 0. So our y-intercept is 0, 0. X-intercept is where the function crosses the x-axis. And so in this case, we're going to flip it and set y is equal to 0. Okay, so we want to set y is equal to 0. That means we're going to have 0 equals x cubed over x squared minus 3. The only way that can happen is if x is equal to 0. So the only place this thing touches the x-axis is the only place where it touches the y-axis, and that will be the origin. Okay, so that gives us one key point that's on our curve. Next is symmetry. Right, so symmetry is about patterns that repeat themselves, okay? And so there's a couple of kinds of symmetry we're going to be talking about. The first type of symmetry is odd, the second is even, right? And the third is periodic. So the way that you want to determine if you have symmetry as far as odd versus even is by finding f of negative x, okay? Now, f of negative x for this function would be, looking at what the function is, let's just replace a negative x everywhere we see an x. How do we find f of 0? We just replaced 0 everywhere we saw an x. Okay, so what do we have here? We have negative x cubed, which would be negative x cubed. Negative x squared is just x squared, and then minus 3. This looks like it's a negative of what we started with. Now when you have f of negative x equals negative f of x, so f of negative x equals negative f of x. That means the function is odd. Okay, what does that mean? To think about what an odd function means, you want to think about an odd powered power function. So like x cubed, for example, looks like this. Okay, so the origin is a kind of mirror, and so the way we go over here mirrors in the opposite sense of what we do over here. So that's an odd function. The other type of situation could have been if we found f of negative x and we saw that that was equal to f of x, right? That's what we call an even function. Okay, so even is when f of negative x equals f of x, okay? And so that's gonna be something like this. What's a typical even function? X squared, right? So what's the symmetry like here? The y-axis is a mirror. So what I see on this side mirrors what I see on this side. That's what it means for f of negative x to equal f of x. That's even functions, okay? All right. And then periodic is trig functions. We'll deal with that, cross that bridge when we get there. Next is horizontal asymptotes. So to find a horizontal asymptote, what do? We need to find the limit as what happens. Yes, as x goes to infinity. X cubed over x squared minus 3. It's going to be limit x goes to infinity of x cubed over x cubed over x squared over x cubed minus 3 over x cubed. We get 1 over x minus 3 over x cubed. It's going to be 1 over basically 0 minus 0, right? Which means we're going off to infinity. Okay. Since that's not a number, so no Donald asymptotes. We see obviously the behavior of this thing is kind of like x cubed over x squared, which is like x, right? So we have what we call a slant asymptote. Instead, behaves like y equals x cubed over x squared equals, well, let's say, which is essentially y equals x. Okay. All right, so since it behaves that way, we'll be able to see that in the big picture behavior of things. Vertical asymptotes. We need to check the following limits. So what limits correspond to a vertical asymptote? The limits that correspond to a vertical asymptote are, if you can find a limit as x approaches a of f of x, and you get some kind of infinity. Now again, that infinity could be a plus or a minus infinity, and this limit could be from the left or to the right. Okay, as long as one of those four combinations happens, you have a vertical asymptote. We know that there's only two places where the vertical asymptote can happen. The only place a vertical asymptote can happen is where you have a gap in the domain, right? So either plus or minus radical 3. Now, not every gap is an asymptote, vertical asymptote. A gap could be a hole. We know it's not a hole in this case because, okay, we know it's not a gap in this case because we are not having the 0 at radical 3 in the numerator, okay? So note that f of x is going to be x cubed over x minus radical 3, x plus radical 3, difference of squares. You got to know your fundamental algebra. And so thus the limit x approaches radical 3 of this, let me just say f of x, what would that be? Well, it looks like it may depend on where we're coming from, right? If we're approaching radical 3 from the right, then I'm bigger than radical 3. Everything's positive. That's going to be positive infinity. Oh, that's all I need. One of the four possibilities happens. We have a VA at x equals radical 3. Okay? By the same token, limit x approaches negative radical 3 of f of x. And let's say from the right again. Okay, in this case, we're at like a negative 1.6 that we plug in. Okay, and so we'd have a negative value. That's negative infinity. Okay. All right. And so we have VA at x equals minus radical 3 as well. All right. So with that, we've done the first half of curve sketching, and but notice that a lot of what we did never used the first and second derivative. All right. What we're gonna do next, we'll definitely incorporate those, and we'll see how that all works together. All right, so we're talking about curve sketching, and we've seen how you start with a function. You want to identify its derivatives, and first and second derivatives correctly, find their zeros. But we haven't necessarily used those results. We shall in this video. Previously, though, we identified domain, intercepts, symmetry, as well as asymptotes, right? So things that we could have done in our algebra course. Now we're jumping into the calculus of things. And first we want to look at the increasing and decreasing nature of the function. To identify where a function is increasing or decreasing, we didn't know where the rate of change is positive or negative, right? Remember, if I'm increasing, okay, function like this right here, I'm increasing along this part of the curve, right? That's where it's increasing. But that's also where I have a positive rate of change. So increasing and positive derivative go hand in hand. Now, where am I decreasing? I'm decreasing over here. I'm decreasing over here. I'm decreasing over here, okay? But that also corresponds to where I have a negative rate of change, right? Where the derivative is negative. Okay, so how am I going to identify these locations, right? It's obviously not necessarily always going to be easy to see on a curve where things change from increasing to decreasing and so forth. That's the power of doing things analytically, right? Because I know things are going to change here from positive to negative. I know they're going to change here from positive to negative. If I'm walking along the number line and I'm changing from positive to negative, right? What do I need to cross? I need to cross 0. So finding the zeros of the derivatives are going to help us identify where things switch from increasing to decreasing and back. All right. So man, I just wish that we would have taken the time to do that before and find those zeros, because if we did, it will make things so much. Well, actually we did. So let's just go back up here and realize that we found the zeros of the numerator and the denominator of our function, 0 and plus or minus 3, as well as plus or minus radical 3, right? So these are the spots where we need to see what is what for our function. So I'm gonna take my number line and basically split it according to the zeros of my numerator and the zeros of my denominator, okay? So we'll go ahead and okay, now my zeros are going to be negative 3 in order. Negative radical 3, 0, we have a radical 3, and we have a 3. So these are all of the zeros of the first derivative, all right, in the numerator and denominator, okay? And so these are the spots that we need to divvy up our number line and identify, what are we doing within these intervals. Alrighty, so I'm going to say right here, this line represents negative infinity. This represents minus 3. This represents minus radical 3. This represents 0. This one represents radical 3, which is this one as well. And this represents 3, infinity. Okay, so we're going to represent these lines of demarcation in the table as well. Okay, so the question is, what's happening to f prime on these places and spaces? Now, recall that f prime was equal to x squared minus 9 over x squared minus 3 squared. It's equivalent to x squared, x minus 3, x plus 3 over x squared minus 3, quantity squared. Now, you're not necessarily going to need to factor it all the way. I like doing it. It just makes things a little bit easier as we proceed and traverse through this rough tundra. Okay, so I am looking at choosing any number over here, okay, between negative infinity and negative 3. Let's choose negative 100. By plugging the negative 100 into this function, I get positive, negative, negative over positive. That's positive. Okay. If I plug in any number between negative 3 and negative radical 3, so let's choose a negative 2. I get a positive, okay, from here. I get a negative from here. I get a positive from here. Okay, so I hope all of this makes sense. And let me undo. Okay, so we got positive, negative, positive, divided by positive. Now the denominator is always going to be positive. Why? Yes, because it is squared, so it's always going to be positive. So I'm not even going to worry about the denominator. I'm just looking at the numerator. Okay, between negative radical 3 and between 0, let's say negative 1, I'll have positive, negative, positive, so it's going to be less than 0. From 0 to radical 3, let's choose a positive one. I'm going to have a positive, negative, positive, okay, which will be negative again. All right, next, from radical 3 to 3, let's choose a 2. We get a positive, we get a negative, we get a positive, that's still negative. Okay, and finally, between 3 and infinity, let's choose a 100, positive, positive, positive. Okay. Alrighty, so positive is same as bigger than 0. That's indicating we have increase, right? So that means the function itself is increase. The derivative is negative in the next interval. That means we have a decrease, right? Decrease. Decrease. Why? Because we learned that if your derivative is negative, you're decreasing. Decrease. And finally increase. Okay. Alrighty, so that's what we have in terms of increasing and decreasing. Now the thing about it is we can use this to help us identify where we have potential maxes and mins. Why? Because if I'm increasing from negative infinity to 3, negative 3, that means I'm going like that. But if I'm decreasing from negative 3 to negative radical 3, now I'm decreasing now, right? So if I'm going from increasing to decreasing, that means we have a peak, right? So a local max. Okay, so that's what we call the increasing decreasing test. Look at where you're going from increasing to decreasing, right? So the function has a local max value of f of negative 3. Okay, so when we plug in negative 3 into our original function, which is x cubed over x squared minus 3, we get negative 27 over 9 minus 3. So negative 27 over 6, negative 9 over 2, negative 4.5. Okay, and that occurs at negative 3. Then I'm decreasing, right? I'm decreasing. So I know that there's not going to be any local maxima or minima, no local extrema between negative 3 all the way until I hit 3. Why do I know something's going to happen at 3? Because at 3, I'm going from decreasing to increasing. So something is going to happen here where that change happens. Alrighty. And so going from decreasing to increasing means I'm going like that, then I'm coming back up. So something happens right there, which is a minimum. Okay, so we have a local min value of f of 3 equals 27 over 9 minus 3, which is positive 4.5. I'm not surprised I'm getting this exact same value. Why not? Because it's something we discovered and determined earlier. What did we just determine about this function, about what f of negative x was and how it relates to f of x? We found that f of negative x was equal to negative f of x, which means the function is odd. So if down here, right, I'm at negative 4.5, then I expect to be at positive 4.5 up here, right, at negative 3 versus positive 3, because it's an odd function, symmetry. Alrighty, that occurs at positive 3. Okay. Okay, and of course, when we say occurs at, we're talking about x location. So let me just make it abundantly clear. That's x equals negative 3. Okay, that's x equals 3. All right, concavity. So you may be thinking that we're talking about, dental work, but concavity has to do with whether the graph of the function opens up, like a bowl that opens up, or opens down. Okay, this is concave up, just like in the word CU, the U is opening up, and this is concave down. Okay, so that's another very important feature of a function that'll give us insight in terms of how to sketch it without even using a calculator. And in advanced mathematics, the idea of concavity is pretty important for some very deep and powerful results. So let's go ahead and check out concavity now. Again, what we're going to learn with the second derivative test is that concavity is determined by your second derivative. A function is concave up where the second derivative is bigger than 0. So concavity is about the second derivative, whereas increasing and decreasing is about the first derivative. All right, and by the same token, they're concave down where the second derivative is, guess what? Less than 0. So what we're going to do here is look at that derivative and identify where is it positive, where is it negative. But how are we going to know where that happens? Okay, so if I have a function and it's doing a little something like this, okay, how am I going to know where it changes? I'm going to know where it changes by looking again at the zeros of the second derivative, right? If I'm changing from CU and all of a sudden now I'm CD, in order to make that change happen, I need to cross 0 because I'm sufficiently smooth, right? There's not going to be any huge jumps here. Our functions are sufficiently smooth, typically, right? And so that's what we're working with. So I need to go back to our second derivative, find the zeros, and then identify what those are. Use that to divvy up the number line. So we just have the positive or negative radical 3 and 0 as our 0, so less than what we had before. So what we'll see is that we'll have basically this interval from here to here, stop, from here to here, stop, from here to here, stop, and from here on to infinity and beyond, right? So we'll have 3 cuts, 4 pieces, right? So let's see how this all breaks down. As we had last time, we're going to say this is negative infinity, negative radical 3, 0, radical 3. This is still radical 3, infinity. Okay. All right, now what was our second derivative? So we need to plug into it. So our second derivative was 6x quantity x squared plus 9. Okay, f double prime was 6x quantity x squared plus 9 over x squared minus 3 to the 4th power. Actually, I'm sorry, to the 3rd power. Because one of them cancels out. So did I put that up here? My bad. This should be to the 3rd power. Because one of those is going to cancel out. Alrighty. Okay, so then let's plug in. Between negative infinity and negative radical 3, we'll plug in a negative 10. That's going to be negative times something that's always positive. Now our denominator is to the 3rd power, and so we do have to plug in. We're going to have something positive. Okay, 100 minus 3 is positive, cubed positive. So we'll have a negative in the second derivative in this interval, which is less than 0. From negative radical 3 to 0, let's plug in a negative 1. We'll have the same scenario on top, a negative times a positive. Denominator this time, however, it will be like 1 minus 3 is negative 2, so that's going to be negative, positive. Okay, from 0 to radical 3, let's plug in a 1. We'll have a positive over a 1 minus 3 is negative 2, so that's a negative. All right, and from radical 3 to infinity, plug in a 10, that's positive. It's going to be greater than 0. Now, if I'm less than 0 for my second derivative, does that mean I'm concave up or concave down? Do I open up or open down? Do I open up or open down? We open down, so that's CD. That's CU. That's CD. That's CU. Okay. And so what we want to do is take all this information and summarize it, which we will do next. All right, so we have completed a curve sketching worksheet for this rational function x cubed over x squared minus 3. We have not used our graphing calculators or computers to identify what this thing looks like, but we have identified so many visual properties of it simply by looking at analytical results, function, evaluations, limits, derivatives, right? So everything we've done in this course to this point, we're doing it all in one problem. So let's bring it all together. What is a domain? We remember that a domain only has breaks at the radical 3's okay, and then radical 3 infinity. Intercepts, we said, well, the only y-intercept was 0, 0, and that was the only x-intercept, okay? So that's that. Symmetry, it was odd symmetry. So we know it's odd. And then asymptotes. The horizontal asymptote equation was none. Okay, but we did have a slant asymptote that y is equal to x. So we'll keep that in mind. Okay, vertical asymptote equations, right? It's going to be, well, what is the equation of vertical asymptote? It's always x equals negative radical 3 and x equals positive radical 3. All right, local extrema. We had a min at 3 and 4.5. And we had a max at negative 3 and negative 4.5. So that right there tells me that the min is local and the max is local, not absolute. Inflection points. Well, what's that? An inflection point is where concavity changes, and it's basically the point that corresponds to the value where concavity changes. So where does concavity change? Concavity changes at negative radical 3, right? Because we go from CD rather to CU. So it changes right here. But we know that at negative radical 3, that is not a point on the curve. But at that location, which we know is a vertical asymptote, concavity changes. So we'll say, negative radical 3. And just leave that blank. Next is 0. So if concavity changes at 0 from CU to CD, but that is a point on the curve. It's the intercept, right? So we'll put 0, 0. And then finally, we go from CD to CU at radical 3. And so therefore, that's another location of inflection. But it's not a location point. It's not an inflection point because, of course, it's not a point on the curve. So we should be able to take all of these facts, along with all of these very specific points, and pin down a look for what our curve should be. Okay. All right. So let's go ahead and break out the ruler. All right. Okay, so as far as points, we know the intercept is right there. Okay. We also know that the locations of demarcation that are going to be critical for this function are going to be negative 3, negative radical 3, radical 3, and 3. All right, so let's see what we got. We have from negative infinity to negative 3, we have an increasing function. that is also going to be concave down. We have something that's increasing, that's concave down. Now it's going to be increasing to -3 and then start decreasing from -3 to negative radical 3 with those asymptotes. Okay, so I got my asymptotes here, and let's actually bring the again. So we got these asymptotes here. Feels good to not be able to mess up a straight line. This right here. So right here is a point, -3, -4.5. Which we said was a max because it's concave down. Then we have +3 and +4.5, which we said was a min because it's concave up over there. Okay. Any other points of notes that we can plot? I don't think so. So I think we're more or less ready to get going on the sketch. Okay. And so we have concave down. And the last thing to remember is that we had some slant asymptotes. So we just keep that in mind as we draw the sketch, kind of like a Y is equal to X look that is associated with this as well. Okay, so our sketch will look something like this. Coming this way, like a Y is equal to X. Then we're there. Go towards the asymptote. Okay, that's my concave down. Right, from -infinity to negative radical 3. Then I'm concave up from radical 3 to infinity. Now, why am I doing that part now? Then going over to my slant asymptotes or something like that. I'm doing that part because I know it's odd, and so I know the left will mirror the right. Okay, from there, I know that I am what's happening from negative radical 3 to radical 3. I'm steadily decreasing, but my concavity is changing from concave up to concave down with the asymptote. Okay, so always decreasing, but concave up. That's decreasing and concave up. Now I'm still decreasing, but now I'm concave down. So that's going to look something like this for this curve. Okay, and so that's what we got. That's our asymptote over here and over here. Slant asymptote going that way. Vertical asymptote over here. Vertical asymptote going down that way. Slant asymptote that way. And that's our function. All right. F of x is x cubed over x squared minus 3. In the place to be. All righty. So that's a complete curve sketching loop. Curve sketching cycle. I will in the next video show you how we can use SymPy to get this done quick, fast, and in a hurry. All right, so let's close the cycle. For this function, we'll be looking at curve sketching. And what function are we talking about? The rational function x cubed over x squared minus 3 has been the star of the show. We ran through derivatives, identified the zeros of the derivatives, numerator and denominator. We looked at the domain, the intercept, x and y. Symmetry, odd, even, or periodic. We notified it was odd, and that helped us with the graph, horizontal and vertical asymptotes. We use the first derivative and the zeros thereof to identify intervals of increase and decrease, and thus local max and mins based on the increasing decreasing test and first derivative test. Then we looked at concavity based on the second derivative zeros and identified where it's concave up, like a U, or concave down, which is the opposite. From all of that, we identified key points on the curve that we could sketch. We brought it all together in this beautiful soiree original. All right, so what we want to do next is we want to shift gears and lean on AI to help us do this thing in Python. I'm going to crack open Colab and spark up a code cell. And what I want to ask it to do is use SymPy. A little bit different than what we did before. We want to see how SymPy works. Okay, so let's use SymPy to find the first derivative of the function. So you have to be a little bit adept with, this LaTeX type of syntax. Okay, and then just to make it clear that we want to do it like this, and the basic thing you have to know is that the caret is an exponent. Okay, so x squared minus 3, bam, enter, and AI does what we need. So we're gonna use what we call the SymPy module in Python, which is a module where a lot of the symbolic calculus is done. Usually when you code and you declare a variable, it takes on a value that's whether a numerical or a word or whatever. But those values are used every time you call the variable. With SymPy, by using the x equals symbols, parentheses, x, that says, you know what, I'm going to use a variable called x symbolically. It's not going to represent a number, it's going to represent itself. And so we can use, like you see here, something like x, and in Python the double star is an exponent, whereas here it's a caret, but here it's double star. And so now since x is declared as a variable, this understands the x cubed over x squared minus 3 from the variable perspective, as opposed to like treating it like plugging in a number. Okay, and then we want to find the derivative of this. So what is the function that we use to find the derivative? Well, just hover over it and you can see some of the syntax in terms of how you find a derivative, right? So the diff parentheses means you're using a derivative function, finding that derivative, calling the result derivative, and then when you write it here, it means we want to see what happens. Okay, this just calculates it. This is I want to see it. So let's press play, import the function. Let's make this thing happen. And here we go. Okay, so that's our derivative. Is that the same thing that we got? What we got for the derivative was this over here. Does not look the same. Okay. And so going back to Python, what can we do? Okay, well, if we just do this, simplify, use that simplify function, you see what we get. Boom. So when we simplify, our numerator now looks a lot more like the numerator we got. Check that out. Boom. Okay, x squared quantity, x squared minus 9. That's that right there. They ended up doing one of the soiree rules that you shouldn't do, which is expand out your denominator. But hey, we'll take what we can get. We already saw that the denominator was the same before. That's our first derivative. Okay, now to find the zeros of the first derivative. Okay, I'll actually do that up here. To find the zeros of the first derivative, instead of simplify, just put solve. And that's going to get you the zeros of your first derivative. -3, 0, and 3. Right? Those are the zeros of our first derivative. Okay? So hopefully that is very clear. Okay? To find the zeros of our denominator, let's actually just start coding. Here's my denominator. I'll copy that. I'll click solve and paste that. Play, and there we go. Okay, so this right here are our zeros. This over here are the places where it's not defined, and that right there gives us the total set of critical points, critical numbers. Okay, now we want to do the same for our second derivative. Okay, so man, I'm polite. Mama raised me right, so I'm gonna say thank you to AI. Now find the simplified version. Okay, as well as its zeros. Sometimes when you give multiple commands, AI starts tripping, but let's see how this goes. Okay, and I did the cardinal rule of AI and Colab, and I did not hit generate first. So let's try this now. Okay. Okay, so boom. See now I have two outputs, the simplified second derivative and the zeros. And the print statement is what's going to allow me to have one code block with two outputs. Let's press play, simplified second derivative, as well as the zeros. Now, because I did print, it's giving it to me in this nasty format. So what I'm going to do is just copy the actual simplified second derivative, right? Which comes from simplify and then using diff twice. And I'll just go ahead and, copy that. Create a new code block, paste that, play that, and here we go. So again, the denominator, when they simplify, they expand it out, which is not a good look. Instead, let's go ahead and look at that numerator, 6x quantity x squared plus 9. What did we get up here? 6x quantity x squared plus 9, so we're on the right track. Okay, so key things with SymPy is diff means derivative of f with respect to x, right? So knowing that x is a variable of differentiation, okay? And again, right here, this tells us some of the syntax of how the diff function works, okay? Simplify was what we use to be able to put things in terms of how we wrote it. Which when you're doing it by hand is what helps you find your zeros much more readily, okay? And then solve helped us find the zeros, okay? And so this right here is just a documentation, really helpful. You see some examples of how to do it. So really helpful in terms of learning how to code. And again, if you can learn not only how to do calculus by hand, but how to check your work by code and to be proficient at code in this AI-driven world, you're giving yourself a competitive advantage and can't be touched. All right, so that completes the cycle of looking at this function right here, both from the standpoint of analytically, seeing what the graph looks like, and then as well as what we have here. So why don't we try to see what the curve looks like, right? Let's close this loop and see what the curve looks like. Like, let's close it. And so I'll say, use matplotlib sketch EFG. Alrighty. So matplotlib works pretty good with SymPy. And that's one sketching library that we can use. And we get something like this. Okay. So clearly not the best with asymptotes, but it's kind of the idea of what we have. In a case like this, tried and true decimals is probably the way to go. Okay, so let's go ahead and do a quick sketch in decimals. Y equals x cubed divided by x squared minus 3. And in place of b, that's what we got. Okay. We see here, as we have our local max here, we have our local min here, exactly what we got. As you trace the curve, looks like we're getting closer and closer to negative 1.7, which is our asymptote, but never reaching it. Same thing over here, positive 1.7, never reaching it. We're increasing all the way to negative 3. Then we're decreasing, all the while concave down. Concavity changes at negative radical 3. But we're still decreasing, right? Decreasing doesn't change. Okay, now we're concave up, now we're concave down. Decreasing, okay? Decreasing, and then concave up. Alrighty, so I know that's a lot, but by doing things by hand, supplementing it with code, you get a really good idea of what is going on with the curve, analytically, from a graphing perspective, and even from a coding perspective. I hope you enjoyed this process. Keep it locked for the next video.